Okay. Yeah, I think we'll start. Sure. So the first speaker for the day is going to be Soumyajit. He'll be presenting his talk titled Existence and Computation of Equilibria in Single Dimensional Movement.
Okay. Okay. So let's start. So yeah, so as you all know that synopsis is happening today. So let's take a hypothetical situation. Though we are not getting these beverages, but let's see. So let's say there are three choices. We have wine, cola, and milk. And hypothetically, let's say only one drink will be served, and there are 7 people. There are more than 7 people. As I didn't expect more than that, but okay, it's fine. So it's early in the morning, right? So now 2 of them have choices like this: wine over cola over milk. 2 of them have choices like cola over wine over milk, and 3 of them have choices like milk, cola, and wine. Now the question is that which beverage should be offered? Okay. So how do we answer this? So let's see some options. So let's see only the top choices. So let's go back. So here, if we only see the top choices, then you can see milk will win, right? Like 2 individuals will prefer cola, 2 individuals will prefer wine, and 3 individuals will prefer milk. So milk will be the winner. But so then milk should be served. But as you can see, like 2 plus 2, 4 individuals least preferred drink is milk, right? So total 7 individuals, more than 50% of the people most choice is milk. So something is wrong. I mean, milk should not be served. So then what can we do? So let's see pairwise comparisons. So what is a pairwise comparison? So basically you choose any 2 pairs. So let's say cola and wine, okay? And just forget about milk. So let's say milk is not in this ranking. So if you see, then like 2 plus 3, 5 people likes cola over wine, right? So then cola wins over wine. So we say cola wins over against wine in pairwise comparison. Also, if you take cola and milk, just forget about wine. Then also 2 plus 2, 4 people prefers cola over milk. Then cola also wins. So basically, in pairwise comparisons, cola wins over every other drink. Then we conclude that cola should be served, and it's good actually. So, as you tell me, why do you say that milk should be chosen? So if you see only the top choices, not this cola. So this choices, just forget about this. Only the top choices, like only the milk, cola, and wine. Then you can see that like 3 individuals prefers milk, right? And I like cola, so yeah, so it's good. So and it's called Condorcet Paradox. Okay, so I'll define what is the Condorcet Paradox or something. So yeah, so basically, as you can see in this example, so cola wins over every other drink in pairwise comparisons, but does it always exist? So does it always exist? I mean, so in pairwise comparisons, some alternative or candidate wins over every other candidate. So yeah, but it doesn't. So here is the example. So let's say there are 3 individuals and 3 choices, and the choices are A, B, C. Let's say the first one prefers, preference choice is like A, B, C. The second one is B, C, A. The third one is C, A, B. So it's like a cyclic shift, and you will get this ranking. So yeah. So then what about pairwise comparisons? So as you can see, A will defeat B, then B will defeat C, and again C will defeat A. So it's like a cycle. So A defeats B, B defeats C, C defeats A. So basically there is no Condorcet. So you can't conclude, right? So but we have seen that Condorcet winner is good. I mean, so and there are some properties of Condorcet winner like strategy proofness and all. I'll not go into that part, but Condorcet winner is a good thing. But as you have seen that in this preference profile, we don't have a Condorcet winner. So can we somehow restrict our rankings in such a way such that there always exists a Condorcet winner? And the answer is yes, we can restrict our domain of rankings, and there are many ways, but we'll see only one way. So let's start. So these are the preliminaries. So you have the set of voters V, set of alternatives A, and each voter I has a total order over the alternatives. That's called pi I. And this tuple, this pi1 to pi n, is called a preference profile. And the voting rule is that you will give, so you will feed this function, this pi, and the function will return only one win. So basically, as you all know that there is a presentation competition is also happening in this STCS synopsium. So that is a voting rule actually. So everyone will, not the preference, I think utility, but you can draw a preference list and find a winner, okay? Okay, so as I have said that, can we somehow restrict our preference profile such that we always have a Condorcet winner? Yes, and this is some realistic way to do that. So this single pick preference profile. So what is a single pick preference profile? So let's see the picture first, okay? So first you'll have a global ordering over the candidate. So like here, you have a global ordering. So A less than B less than C less than D up to G, okay? Now, so this, so these lines are the ranking of each voter. So let's say, so let's talk about this blue voter. So the blue voter's top choice is D, okay? Then, as you can see, when B, so then E is ranked higher than F is ranked higher than G, and vice versa. And also from this side, C is ranked higher than B is ranked higher than A. So here is the definition. So preference list or ranking is single pick with respect to this ordering, this global ordering. Whenever so this top I means the top choice of the ith voter. If top I less than A less than B, or top I is greater than A greater than B. So see this. So this is the green one. I mean the global one. Okay, is B, then A should be ranked higher than B. So here, as you can see, the top choice of the blue voter is D, and as E, F, G are ranked like this in the global ordering, then E should be ranked higher than F should be ranked higher than G. And also C should be ranked higher than B should be ranked higher than A. But there is no relation between this C and E, maybe C and F. There is no relation. But in this side, it should be in the decreasing order. In this side, they should be in the decreasing order. Also, let's see this brown voter. So its top choice is C. Then D should be ranked higher than E should be ranked higher than F, and F should be ranked higher than G, and then also in this side B should be ranked higher than F. But there is no relation between B and D, B and E or what. Okay, so this is called a single pick preference profile. And so a preference profile is called single pick if all the voters ranking is single pick with this global ranking. Okay, so let's see an example. So here's the example. So let's say, so this is a line over here. So these circles are the voters and the triangles are the candidates. And the preference of each voter is proportional to the distance of the candidate. So the preference of V1 should be C1, C2, C3. Preference of V2 will be C2, C2, then C3, then C1. And the preference of V3 will be C3, C2, C1. Okay. And as you can see, it's a single pick preference profile. Why? Because see here, V2 top choice is C2. So what is the global ranking here? The global ranking is C1 is less than C2, C2 is less than C3 in the real line. Okay. And you can also think about vice versa. And see, C1 is greater than C2, C2 is greater than C3, whatever. But as you can see, V2's top choice is C2. V1 top choice is C1. And as the global ranking is C1 is less than C2 less than C3, then C2 should be ranked higher than C3. So V1's preference is C1, then C2, then C3. And also V3's preference is C3, C2, and C1. And for V2, you can, so here as it's proportional to the distance. So that's why I have written the top choice is C2 and then C3 is closer than C1. So C3 and then C1. That's it. So it's a single pit preference profile. But there is a thing. As you can see, C2 is a Condorcet winner here. You can just check. C2 is a Condorcet winner. And also V2 is a median voter and its top choice, the C2, is a Condorcet winner. So here is the theorem. I will just state it properly in the next slide. So the theorem says in a single pit preference profile, the median voter's top choice will always be the Condorcet winner. There always exists a Condorcet winner in the single pit preference profile, and it is the median voter's top choice. Okay. But as you can see, this is a special case of single pit. I mean, I have given you a picture and then, so, I mean, this is a special case of single pit, but in the broad sense, what is a median voter? So that I will define here, some theorem. So let's say you have a global ranking. So just like the green one. So yeah, this green ranking that is called R here. So you have a total order over the alternatives. And the preference profile is single pit to R. Then what you do is that you sort all the voters. You sort all the voters according, so by R, by the global ranking, according to their top choices. So you go to every voter, see their top choices, and I mean, and compare it with R, and then sort them. Then the median voters' top choice will always be the Condorcet winner. And this is the median voter here. And it's easy to prove actually, so I have omitted the proof. So yeah, this is the median voter theorem. Great. But in real life, what happens? So in real life, voters do not submit their whole preference list. They just vote for one candidate, their top choice. So then what should we do? Okay. So let's take another example. So it's a very good motivation for our problem. So let's say there is a highway. So you consider a highway as a real line. So interval on the real line. So let's say 0, 1, this interval. And there's a locality around the highway. So as you can see, I mean, a real line, and you know that in this point there is, I mean, 15 people lives here, 20 people lives here. So they are called the individuals. And certain companies want to build restaurants on the highway. Okay. So basically each company want to build one restaurant along the highway. Okay. And their aim is to optimize the number of customers visiting their restaurants. Okay. And I mean, people will go to their closest restaurant. So as you can see, let's say the restaurants in Colaba is extremely expensive. Okay. As you can see, if you go to Powai or some, let's say Navi Mumbai or Vashi, the restaurants are good and also not that much expensive. But but often we just go to the restaurant for Colaba, not to Powai or something, because they are closer. So the customers will go to their closest restaurants. So now the utility of every candidate or the restaurants is to optimize the number of customers. So what approach should we use for modeling this? Okay, so let's take a game theoretic model. So it's like the voters are distributed along the real line and they are static. So the voters are the people lives on the real line. The candidates are the restaurants actually. So they choose their position on the real line. So it's their strategy. So they choose a point between 0 to 1 interval. Okay. And the voters will cast their vote for the closest candidate. So here vote means that I will go to that restaurant. That's it. And each candidate wants to maximize their vote share or the utility. Okay, so let's take an example. So here,
like the voting is completely determined by the distance.
Yes, exactly. So if there are two restaurants, closest to the same point, then half of the people will go to this restaurant, half of the people will go to this restaurant. Okay, so that's right. So let's take an example. So here, so these are the people, so these circles, and these are the restaurants, let's say, these triangles. Okay. So as you can see, C1 will get 2 votes. I mean, these two individuals will go to this restaurant, C1. C2 will get one vote, and C3 will get 2 votes, right? Also, the median voter stop choice, C2 is not the winner, but it is not, I mean, we will not go to that part, but we will go to a different path, that is it a Nash equilibrium? So basically, these are the players, and C1 is there. So C1's utility is 2, C2's utility is 1, C3's utility is 2. But is it a Nash equilibrium? Definitely not. Why? Definitely not. Why? Because C3 is getting 2 votes, but C3 can move to this position V3, and its vote will increase to 3, right? So now C3 is getting only votes from V4 and V5. But if he moves towards V3, let's say onto V3, then V3 will also vote for C3, V4 will also vote for C3, and V5 will also vote for C3. So its vote share strictly increases. So it's not a Nash equilibrium, right? So here is the question: does there always exist a pure Nash equilibrium? And can you decide or determine it in polytime? Okay. Okay, so these are some previous works. So these authors actually analyze the US voting system. So they have had kind of a bimodal normal distribution. So why bimodal? So they have analyzed the ideological distribution of the voters. So one peak is for Democratic, one peak is for Republic. Okay, and there are only 2 candidates, and they have just analyzed the quality of the Nash equilibria, or how to compute a Nash equilibrium on that. There is another paper that actually, so in this paper, they have done something quite interesting. So first you are given the whole preference profile, and then they will embed these voters and candidate into some metric space. And the main goal is to optimize. So actually to find a voting rule that actually selects a candidate with the least total distance to all the votes. Okay, so actually the embedding process follows this rule actually. So the voters assigns higher ranking to the candidates closer to them. So you have to embed the voters and candidate in such a way that the ranking of each voter should be proportional to the distance of the candidates. Okay, and then you have to find a voting rule that selects a candidate the least total distance to the voters. Okay, and there is, so this work by Harold Hope.
You can move both the voters as well as the candidates.
No.
It was saying in the matrix that
No. So whenever you embed, it's done.
okay.
It's done. Then you have to just find a voting.
It is always possible that you are given, let's say, 2 candidates, and voters are giving their preference rule. Some candidates and some voters, and they are given their preference list, and now you want to embed them so that this.
That's the thing. Yeah, that. So you are given the ranking first, and then they will embed such that it is consistent with the ranking.
So it's always possible to write such a.
Yeah, that's the question. But so the dimension matters, right? I mean, in which.
Is there always a matrix?
I don't know. I mean, in this paper they have done it, but yeah, I haven't seen that. But yeah.
Okay, so also the goal is then assuming that it can be embedded in some matrix.
Yes.
And then it's assigned according to the order.
Yeah.
So you want to find the least total distance again. So they show that this is always possible.
Again, the last line.
So they show that it's always possible to find the least total.
No.
Only in the ordering.
No. So they will define a notion called distortion, and they will show that the distortion is 3.
Also, you find a candidate which is at most twice to these two.
Okay. That is always.
Okay, so this is actually very close to our problem. So by Harold Hotelling. So yeah, so here, so our distribution of the voters is discrete, but Harold Hotelling so has taken a model where the voters are the voters distribution is continuous, and there are only two two candidates or two restaurants, you can think, and he wanted to find some equilibrium, but there he saw something. So in the model, they considers, so the features and prices, but also on the seller's location. So the decision of the consumer also depend on the seller's location. That I have seen. So that I have already told about this Kolaba and Powai, right? And the equilibrium also, largely depends on the travel costs. Okay. So let's take so what is the results of so the results of us on this model? Okay, so the model was this, as you can remember. So this thing. So a real line, you have voters on the real line, these circles, and the candidates are the players, and they want to choose their position on the real line such that their vote share is maximized, and you want to find a pure Nash equilibrium. Okay. So here are the results. The first result is that, so basically for two candidates, there always exists a Nash equilibrium. Why? I mean, the two candidates can go over the median voters position and on the median position, and whoever wants to deviate will get less than 50% of the vote. Okay, so for two candidates, and as you can see, the previous papers mostly worked on this two candidates cases, but we have showed in so this is actually my master's thesis. So in my thesis, I have shown that for three candidates, there exist some examples you can construct where there is no pure Nash equilibrium. Okay. Now the next result I will prove. So for less than 5 candidates, so up to 4 candidates, deciding the existence. So as you know that, I mean, in many cases there doesn't exist a pure Nash equilibrium. So now this is the result that for less than 5 candidates, deciding the existence of pure Nash equilibria is quality uncomputable. So let's see the proof actually first. So here is so we'll prove this. So for 3 candidates, it's easy actually. I mean, so the same proof will go on. So we'll just prove for the four candidates. So for 4 candidates, deciding Pyne for a given instance is quality uncomputable. So how do we do that? So we'll prove this claim. So for 4 candidates, if there exists a pure Nash equilibrium, then there exists another pure Nash equilibrium where all the candidates are on some voters location. So basically this. So yeah, so basically it's saying that if there exists a Nash equilibrium in this case, so then there exists another Nash equilibrium where all these candidates, the C1, C2, C3 are not on these continuums, are only on these circles. Okay, so this is our claim. So as you can see, this claim, so this claim actually directly implies that this is quality uncomputable. Why? So basically each candidate will have n choices at most. So there are n to the power 4 configurations to check. And in each configuration, you will check that if it is a Nash equilibrium or not. Again, I mean, checking a Nash equilibrium can be harder. I mean, may not be quality uncomputable, but that is another result. I will show that result in a later slide. But let's prove this claim. Okay. So to prove this claim, we'll assume this lemma. So this lemma is a little bit hard to prove and also very rigorous. So I have just omitted the proof. So this lemma is saying that so if there exists a pure Nash equilibrium, then there exists another pure Nash equilibrium where the extreme candidates, the extreme candidates are the leftmost and the rightmost candidates. So here, so here, as you can see, the leftmost candidate is C1 and the rightmost candidate is C3. So these are called the extreme candidates. So the extreme candidates will always be on some voters location. So the leftmost and the rightmost candidate will always be on some circles. So if we assume this, then the proof is easy. So this is the proof sketch. So let's say so we know that the leftmost and the rightmost candidate will be on some voters location. So now let's say there is a candidate J who is not on some circle but on this interval Li and Li plus 1, and this is a pure Nash equilibrium. Okay, now we will construct another Nash equilibrium where this candidate will be on the circle, on some circle. Okay, yeah. But as there are 4 candidates, you can see that J will always have either a immediate right extreme candidate or a left extreme candidate. Okay, as there are only four candidates. So without loss of generality, let's say J has the immediate extreme candidate, right extreme candidate, and that is JR. Okay. Now all the voters between J and JR should vote for JR. Why? Because if not, then JR can just switch its position to Li plus 1 and can snatch all the votes from J. And then the previous, this configuration is not a pure Nash equilibrium, right? Then all the voters here should vote for JR. Then also you can see Li should also vote for J. Why? Because J is not getting any vote from this side. So if Li also doesn't vote for J, then J is getting 0 votes. And clearly it's not a pure Nash equilibrium. Then we can just move J to Li and nothing will change. Because all the voters in Li is voting for J. And if you just move J to Li, then nothing should change, because if J gets more votes from the left side, then this configuration is also not a pure Nash equilibrium, right? Then we can just move J to Li and the resulting configuration. So there is some subtle cases I have just omitted, but basically this is the proof sketch. So you can just move J to Li and the resulting configuration will be a pure Nash equilibrium. Okay. Okay, so the 4 is, so basically you have 4 candidates and you know that you have a leftmost candidate and the rightmost candidate, and they will always be on some voters location. Yeah. So the middle, so whoever is not on the voters location, it will have at least immediate right extreme candidate or a left extreme candidate.
Five candidates, you know that do not exist in equilibrium where all of them are on the voter.
Yeah.
You can't really, it's like they enumerate all possible.
No, he is asking about the proof technique. So in the proof technique, as you can see, so here, you know that there is a extreme candidate here, there is a extreme candidate here. And between these 2 extreme candidates, there can be at most two candidates. Now, let's say one of them, this J, is not on the voters location. On the continuum. So but as there are 4 candidates, you know that J will either have a right extreme candidate or immediate right extreme candidate or an immediate left extreme candidate.
Okay, the terminology you are going to explain. What you mean is J will have some extreme candidate
Immediately.
Most or rightmost.
Yeah.
To their immediate candidate.
Yeah. Their immediate left order.
But can't you then do it one by one from the, let's say, the rightmost and then the second rightmost and the third rightmost?
But our lemma is suggesting that this leftmost and the rightmost will always be on some voters location.
Yes.
And the proof goes like this, that if you, so let's say someone is not on the circle, then we can move it to a circle. That's the thing. Yeah, so for 5 candidates, for 5 candidates, what can happen? For 5 candidates, this proof will not go. Why? Because, so let's say J is in the middle, and here is 2 candidates, and here is also two candidates. So J will not have an immediate right extreme candidate or an immediate left extreme candidate for 5 candidates. So, but for 4 candidates, you'll always have either an immediate right extreme candidate or an immediate left extreme candidate.
The issue comes to a particular location that could be mine.
So here, when we move J to the left, the reason we can move it is because all of the ones which are on the right are voting for the extreme right.
Yeah, this one.
And they are voting for extreme right because he is extreme right.
No, but you could also go to that location and share half of the votes.
But we have to maintain a pure Nash equilibrium, right?
The reason one would be correct.
Yeah, so if you just move it, so if someone was, so you are saying that we can move it to here, right? In the right, then we'll snatch something from here, and maybe it is not a pure Nash equilibrium. But we have to construct a pure Nash equilibrium, and it's safe to go in the left because you have a right extreme candidate. Okay, it's safer to go left. That's the thing, and the proof works actually. And Yeah, so, and also I have asked that, so from this claim, we know that there are n to the power 4 configuration, and you will check each configuration is a pure Nash equilibria or not. So the question is that if the pure Nash equilibria, I'm checking pure Nash equilibria is polytime computable or not, and that is in our result. So basically, yeah, so basically this one. So you can find the best response of a candidate in polytime. So basically, in a pure Nash equilibria, you know that every candidate is playing their best response against other candidate. So, and as you can find the best response of a candidate in polytime, then you can just check that if it is a Nash equilibria or not in polytime. So basically, for more than 4 candidates, we don't know. So we have an example where this algorithm will not work. So sorry. So this algorithm is saying that you just iterate over all the configurations. But for 5 candidates, we have an example where in every pure Nash equilibria, at least one of the candidate will be on some continuum. So basically, you can't iterate over the voter's location. And basically, for 5 and more candidates, we don't know if the problem is computable or not. We don't have an algorithm to decide. I mean, forget about exponential or what. We don't have an algorithm for it. Okay, so it's still open. And so basically, this will be our future work for more than 4 candidates, and try to generalize the problem to D dimension. So it's just one dimensional, but we can just generalize it to D dimension. And yeah, it's end scale. So any questions?
No, but one, the function that you said you can define as the
Function means which? Huh?
for the metric spaces, say,
Huh?
is that function independent of the metric space? Say, how you take the orderings and then compute the point, is that dependent on the metric space, or is that independent on what metric space you embedded?
So basically, I think you are saying about this. This thing, right? So you are saying that in the metric space, so the function that actually embeds this voters and the candidates, are they
So you said the main goal is to kind of
voting goal? Yeah.
Yeah, so that computes like 2 times the row, these kind of distance.
Yeah.
So is that like, how you do that, is that independent of the metric space or?
Oh yeah. Actually, I don't know. I haven't read that paper properly, so I don't know. So there is a voting rule called plurality veto that will actually does that. But I don't know if this is dependent on a metric space. I don't know. Yeah. So Umang, do you know something about it?
It's really not.
Matrix. Okay.
It was from the given.
No, so what I heard is like the voting rule is you want to say the candidate but like, so now when the voting rule only takes an ordering, right, of the destination. So is that voting rule actually caring about what metric space it's embedded in? Or just
No, yeah,
it's just embedded in some.
It says all possible metrics. It will be at.
Yes.
Yeah. Yeah. So more questions? No? Then yeah. Thank you. Next.